Good evening everyone. This is Soni Prajapati from IIT Hyderabad. I am working with Dr. Anupam Gupta and my collaborator Dr. Akshay Bhatnagar. So the title of my talk is Exploration of FIPS, Investigation of ABP System in 2D Background Flow. So the key point here is we'll understand the FIPS and we already aware of active Brownian particle system and 2D background flow we'll get to know. So before going to the actual presentation, we can look at this video where we see there are biological systems which are present in fluid media in a water. So how one can model such kind of system with the help of active Brownian model. So I am not going to introduce about the active matter, already we know. But interesting thing is the length scale of this active matter system vary from nanometer to kilometer, and we can see that mostly this particle behave some kind of cluster behavior, and which is commonly known as MIPS, motility induced phase separation. So I am going to introduce the active Brownian particle, a particle which is having radius A, having the dynamics like this, where the velocity contribution having three terms. One is the self propulsion, another one is the interaction term, and third one is the translation noise, which I am not considering in the system. And the force of interaction is given by this equation. It is also having rotational rate, which is nothing but the random fluctuations. Interesting term is the packing fraction, which is the ratio of total area occupied by this active Brownian particle to the given area. So if I take the packing fraction 0.3, I see that mostly these particles are randomly distributed, and I say them as MIPS, mixed or homogeneous. But as I increase the packing fraction to 0.7, I see these particles are forming some kind of clustering, and this is due to motility, and that's why we called as motility induced phase separation, which is very well known also in these given references. Now I introduce the background flow, and the component of velocity is given by this. Then in the particle dynamics I introduce u, r, I, t, which is coming from the background effect from the background flow, and in the rotational rate it is coming half omega ri, t, half is coming from the Jeffrey equation for this kind of particle. So the dimensionless input variable which we are using here, we got is the scaled velocity, which is the ratio of self propulsion of particle to the scaled velocity of a flow, and the scale time, which is the omega f by nu r. Now with that kind of velocity field, we will get this kind of velocity profile. So where we can see there are 4 vortices, 2 are moving in a clockwise, 2 are in anti-clockwise, and the scale bar is giving their magnitude. So by keeping the scale time constant, if we vary the scale velocity, what we observe for larger scale velocity, this particle doesn't bother about the flow, they just do random motion. But as I decrease the scale velocity, these particles are getting affected by the flow. So at scale velocity 0.4, which is nearly equal to 1, we see this kind of clustering, which is very different from the MIPS. And this is due to the flow topology, and that's why we called as flow induced phase separation, in short FIPS. So now I vary the different scaled velocity. Without background flow, I see with different scale velocity they are forming some kind of clustering, and it is due to mix, and it is due to motility, commonly known as MIPS. But as I introduce the background flow, what I observe that at low tau value, it is either showing MIPS or mixed region, there is no clustering at all. But as I increase the high tau value, I see three different kind of phases. One is the MIPS for larger scale velocity, FIPS for moderate scale velocity, and MIX for very low scale velocity. The color bar is showing the cluster size. So we are getting MIPS like this. Why it is not? FIPS like this, which is different from the MIPS, and then next one is the mixed region. So to identify this different type of phases, we introduce two parameters. One is the correlation between flow and particle, and we understand that in the mixed region and in the FIPS region, we'll see there is a correlation, while in MIPS region we won't see any correlation. Also, we calculated the Ukobo-wise parameter, and it will tell whether these particles are in the strain dominated region or not. Next, we see that there are red square, green triangle and blue squares. These are the real snapshot data, which is showing the three different phases, and the shaded region we got from the support vector machine, which is helping us to clearly identify the boundary of these phases. Further, with the help of this order parameter, which is a combination of Ukobo-wise parameter and the correlation, we are able to distinguish three different phases. So in short, I will say that we got three kind of different phases, and the order parameter will tell which phase is this, and this paper is on archive. One can look at it. Now I am interested to explore the FIPS in more detail by changing the tau value, which is coming as Peclet number. So we are varying the Peclet number. We are going from lower Peclet number to higher Peclet value, and what we observe, as we increasing the Peclet value, we are seeing a clear FIPS. Now we are also interested to know how FIPS is dependent on the different packing fraction, and what I observe that yes, FIPS depends on the different packing fraction. At packing fraction 0.5 or less than that, we see mostly homogeneous kind of distribution, but as it is increasing more than 0.5, we see clear FIPS. And after that, we also calculated MST and number fluctuation. So in the conclusion, I got three different phases, and order parameter will tell where I am. The novel phase is coming at this value where tau is greater than 1 and scale velocity is nearly equal to 1. Also, we understand that with increasing Peclet number and packing fraction, we see a more clear FIPS. Thank you for your attention. Thank you.
Any questions?
Any question, suggestion, comment? Always welcome. Yeah. So actually, there is some structural difference between MIPS and FIPS, which we reported. I will just go quickly. In this paper. So how the how arrangement is varying, like in the term of G of R we have calculated, then we also calculated the MST, number fluctuation and other different parameters just to check whether FIPS is really different from the MIPS.
That is how you differentiate
yes,
between
yes,
these two.
Exactly.
So there are some set of parameters.
Yes, yes. Thank you.
So if I understood correctly, it depends on the ratio of drift to diffusion as well as packing fraction.
Not only that, it also depends on how the flow profile is.
What do
So
you mean by
FIPS
flow profile?
Yeah, so you can see that we have used this kind of velocity component, which is giving this kind of flow profile. So if instead of 4 vortex I am taking the 16 vortex, then um, the way it is arranged, it will be different. Yes.
So let's thank the speaker.
Thank you.